Hi, this is a continuation on page 28 of the complex numbers booklet. We're looking at example 5. Now, if z equals 1 plus 3i, find the smallest positive integer n for which zn is real and evaluate zn for this value of n. Now, this is similar to the question that we did on the page before. Also show that there is no integral value of n for which zn is imaginary. So, if you see this question, what might be the first thing you might want to do with it? See, we've got it. So find the smallest positive integer n for which z to the power of n is real. Now, when you work with powers of complex numbers, you can't do it in the x plus iy format. It's got to be in the mod arg form. Okay, so anything to the power of n, you must put in mod arg form and use de Moivre's theorem. That's the only way you can do a complex number to a power. Okay, so we'll do that. So I'm just going to put let z equal r cis theta. Now let's work out what r is. Isn't it? R is the mod of z, which is the square root of. Do you know what we're doing? You know how we can just draw where it is as well? So we can just go 1 plus 3i would be up here. And we draw out a nice little right angle triangle. Okay, how do we work out z? Actually, is that a root 3 there or just a 3? I'm just actually going to check that. I think there's meant to be a root 3. Just let me check it. A little error in this question. It should be 1 plus root 3i. So I'm going to have to fix that. So can you please fix that? It's 1 plus root 3i. So if z equals 1 plus root 3i, find the smallest positive integer n for which z to the power of n is real. So as I said before, we're working with powers of n, so we need to put it into mod arg form, and we need to apply de Moivre's theorem as well. Okay, so there we go. So r equals mod z, which is, we good? 1 squared plus root 3 squared, which is root 4, which is 2. Okay, so that distance there is 2. Remember, we need to work out tan theta. So tan theta is root 3 on 1, which is 60 degrees, which is oh, sorry, I shouldn't write that there, root 3 on 1. So therefore theta is 60 degrees, which is pi on 3. Okay? Next, therefore you can express your complex number in mod arg form. Therefore z is 2 cis pi on 3. Okay? Now, we need to come up with an expression for z to the power of n. So using de Moivre's theorem, z to the power of n, isn't it 2 to the power of n cis n pi 3? This is by de Moivre's theorem. Now let's just open up what cis n pi on 3 means. It's 2 to the power of n cos n pi on 3 plus I sine n pi on 3. Looking back at the question, we've come up with an expression for z to the power of n. We have to find the smallest positive integer n for which zn is real. Now, if zn is real, there is no imaginary component. See, it'll just be 2 to the power of n cos n pi on 3. So what we need, so for zn to be real, then the sine n pi on 3 has to equal 0. Does that make sense? Yeah. Thereby eliminating, meaning that, thereby eliminating the imaginary component, the imaginary part. So it'll be I times 0, okay? Now, I'm going to do a quick sketch of the sine curve up here, and that's the sine curve there. See, we want sine of 0 or sine of pi or sine of 2 pi. They will give me, see, sine of 0 is 0, sine of pi is 0, and sine of 2 pi is 0. So what would be, I can't put n is 0 because I need the smallest positive integer n, so n can't be 0. If n is 1, I'd have 1/3 pi. If n is 2, I'd have 2/3 pi. If n is 3, I've got 3 pi on 3, which is? What happens if n is 3? Pi. And sine of pi is 0. So that n equals 3 is the smallest positive integer n, which will eliminate the I sine n pi on 3. So when n is 3, we go sine of 3 pi on 3 is the same as sine of pi, which is 0. So therefore n equals 3. So I'm running off screen. Therefore n equals 3 is the smallest positive integer for which Zn is real. Now, in brackets, if you just want some explanation down there, that's because, for example, if n is 1, you get sine of 1 pi on 3. That does not equal 0. If n is 2, I get sine of 2 pi on 3. That does not equal 0. Do you get the idea? But sine of 3 pi on 3. So can you sort of see the pattern? You just need to balance out that divide by 3 with a times 3 on top and get 3 on 3, and you'll end up with sine pi. But also, you really need to sketch the curve, the sine curve, to know that it's pi that you're looking for. And also it says the smallest positive integer n in the question, so it can't be n is 0. All right, it's got to be a positive integer. So you've really got to look at that question very, very carefully. Okay? Okay, so then it says, so evaluate Zn for this value of n. So let's evaluate Zn. So Z cubed is, what do we get? Is, where are we? 2 cubed cos 3 pi on 3, we know that we get 0 for that other bit, plus I sine 3 pi on 3. So when n is 3, I'm just going to write, so when n is 3, Z cubed is that, which is 8. Now cos of pi, just drawing the cos curve up here, what's cos of pi? Yeah. So cos of pi is -1, so it's 8 times -1 plus 0. In other words, its value is -8. So it does say that. Evaluate Zn for this value of n. Then it says, so that's the first part of the question. Are we okay with this? Then the next part of the question says, show that there is no integral value of n for which Zn is imaginary. So now we're trying to make Zn imaginary. So if Zn is imaginary, so the next bit, if Zn is imaginary, now I'm going to write what Zn is under here, 2 to the n cos n pi on 3 plus I sine n pi on 3. If Zn is imaginary, wouldn't cos n pi on 3 have to equal 0? If Zn is imaginary, cos of n pi on 3 has to equal 0. Now, I'm just going to draw a little sketch, one sec, of the cos curve. We've got 2 pi, pi. What we're going to do here, we're just going to explore. So we're trying to see if we can ever get cos of n pi on 3 to equal 0. That way, if cos of n pi on 3 is 0, then our complex number will be purely imaginary. It won't have a real part. So let's look at when n is 1, what do you get? So for n is 1, 2, 3, etc. Don't you get cos pi on 3? Now that's not 0. Cos pi on 3 is what? That's cos of 6. Anyway, it's not 0. I'm just going to put not 0. Cos of 2 pi on 3, that's not 0. See, we need cos pi on 2. So what we're looking for, what we know is that cos pi on 2 or cos 3 pi on 2, the next one would be cos 5 pi on 2, etc. Those are 0. Cos of pi is not 0. It actually equals -1. The next one would be cos of 4 pi on 3. That doesn't equal 0. Only does cos of pi on 2, comma, cos of 3 pi on 2, cos of 5 pi on 2, etc. equals 0. Does that make sense? But we can't just do it like that. We need to have a formal mathematical. You could try it if you can't think of anything else. But what we're going to do, we're going to use our 3-unit general solution results. So to show this more formally, to show this formally, we're going to use general solutions that we learnt in 3-unit trigonometry. The extension trig, okay? Now the general solution that you know, so the general solution definition for cos is this. If cos alpha equals cos theta, do you remember this? Where alpha is acute, then theta, the general solution, is 360n plus or minus alpha. That's actually the general solution rule for cos. It's stated like that. If cos alpha equals cos theta, where alpha is acute, then theta equals 360n plus or minus alpha. Now, if I put that in pi, it would be theta is 2 pi n plus or minus alpha. Now, what you're trying to solve is the following. That's the rule. This is what we've got. We've got if cos of n pi on 3 equals 0. Now, cos of what is 0 according to this graph? Your first value where cos of something is 0. What is it? 90 equals cos 90 or cos pi on 2. See, this is what we've got. If cos of n pi on 3 equals cos pi on 2, then I'm just going to put the n pi on 3 equals, actually I should have here cos theta equals cos alpha, but it doesn't matter. Same thing. If cos theta equals cos alpha, where alpha is acute, then theta is, that's better. So n pi on 3 will be 2 pi n. So this is my theta, this is my alpha, you know, alpha's acute. That's the first value that gives me cos, because see, I've got cos of n pi on 3 has to equal 0. Maybe I should write that first. So in there, what I'm trying to solve is cos n pi on 3 is 0. Now to write that as a general solution, I write it has to be in this format, cos theta equals cos of something. So I write it as cos n pi on 3 equals cos pi on 2. So that's the first time where I get cos of something is 0. So then I get, here's my general solution, it's 2. So my theta, which is that's my alpha. So therefore theta is 2 pi n plus or minus pi on 2. Now I'm going to go for one sec. So I'm trying to find the smallest integer n, so I'm going to make n the subject. So I'll multiply this side by 3 and divide by pi. Does that make sense? So I'll multiply by 3 and divide by pi. So what will I get? 6 pi n on pi plus 3 pi over 2n. No, 3, sorry, not 2n, over 2 pi. Yes, plus or minus, thank you. So I'm multiplying by 3 and dividing by pi, aren't I? Yep. So I've got 6 pi n, I'll make this bigger, over pi plus or minus 3 pi over 2 pi. So I get n is, what do I get? 6 plus or minus 3 on 2. Now, if n is 1, for example, what do you get? 6 plus 1.5 is 7. If n is 2, you get 12 plus 1.5 is 13.5. That will never be a whole number, an integer. Do you get it? See, no matter what values of n you substitute, so we write which can't take on integral or integer values. You can go, for example, when n is 1, you get, sorry, oh, actually I should put a k or something here. I might just put a k because that n and that n are different. So I'm just going to put this as a k. Sorry, girls. Okay. So, for example, when k is 1, I get n is 7.5. If k is 2, sorry, running out of room, I get that it's 13.5. N is 13.5, etc. Okay, so that is now formally showing with the general solution using integral values. And I just have to give it another pronumeral here because I can't substitute n and get an n here. I've just called it k, okay? So I should write that here. I should put here where k equals 0, 1, 2, etc. I'm allowed to have a 0 for this k, but not for that n, all right? Because if it's 0, it gives me the first value you could possibly get. Sorry, I ran out of room there. So a bit of a tricky one, that one. Page 29 now. So geometrical representation of products involving complex numbers. Apply two complex numbers, for example, if you've got a complex number z and you multiply it by a real number k, then let's say I've got the complex number z, so z equals x plus yi, just watch what I'm doing, but I should really have it in that other format, shouldn't I, which is z equals r cis theta. So wouldn't kz just be, wait a sec. We're going to discard that. We're actually just going to do it down here because the explanation is actually here. So normally, if you multiply two complex numbers, don't you multiply the moduli and add the arguments? Yes. So arg of kz will be the arg of whatever k is plus the arg of what z is. Now, if k is a positive real number, I'm going to draw it over here. It would be sitting on the x-axis over there. That's where the real numbers are and the imaginaries are here and the complexes are there in between. Get it? So this x is your real axis. So if k is a positive real number, then the arg of k is the angle that k makes with the positive direction of the x-axis, which is, there's no angle. See, your complex number might be here and you've got that angle theta. This might be your complex number z, right? But k is just like the point 3. It's got no angle with the positive direction of the x-axis. So arg of k is 0. Do you get that? You sure? Because when you draw a complex number, you put it out there in the xy plane and you draw a right angled triangle and you work out tan theta. That gives you the argument when you work out theta. But k is just here. You can't, and I'm not sure how far along, but you can't, it's not a complex number, it's just a real number. It's got no I component, a real number. So if k is a positive real number, then the arg of k will be 0. And so arg of kz will be just z. In other words, if you multiply a complex number just by 2 or by 3 or something like that, it just makes it longer. It's still along the same angle, it'll just get longer. Okay, the argument will stay the same, the angle will stay the same. All right, so for example, if that's z, 2z would be out here just twice as far. Okay, now if k is a negative real number, then k would be sitting over. If it's a negative real number, k is sitting over there if it's negative. And the argument is the angle from the positive direction of the x-axis. Doesn't have to go the positive that way. It can go either way. But what's the angle from there across to there? Pi. Positive pi or negative pi, it doesn't matter. So if k is a negative real number, then the argument of k is pi. So therefore, arg of kz will be the arg of z plus the arg of pi, no, plus the arg of k, sorry, plus the arg of k, which is arg of z. We don't know what it is, so we call it arg of z. We know that the arg of k of this new one, if k is negative, a negative real number, is pi. Now, arg of z is a positive value, and pi is positive as well. So if I go that theta plus pi, don't I go past pi? So I have to subtract 2 pi because I know that pi plus the arg of z, even if arg of z is in quadrant 1 or 2, it doesn't matter where it is, When I add this angle to 180 or to pi, I'm going to go past pi. So remember, that's not a principal argument anymore. Arg of z plus pi is not a principal argument anymore. So I have to do arg of z plus pi minus 2 pi. Okay, now that is just arg of z minus pi. Okay, we can just write it like that. So what I'm doing here, you wouldn't learn that off by heart, all right? Because it's just too much to know. Now, the modulus of kz is the same as doing the modulus of k times the modulus of z. So what we're doing, we're multiplying our complex number z by a real number k. When you do that, you've got to see what happens to the angle, and then you've got to see what happens to the modulus, because your complex number will be in mod arg form. So we've just discovered here what happens to the argument, to the angle. So if k is on the positive real axis, the argument stays the same. And if k is on the negative, is a negative whole number, then the new argument will be whatever the original argument was minus pi. You don't learn it off by heart. You just should be able to work it out, okay? Now, that's what happens to the argument. What happens to the modulus of the new number? The modulus of kz. Now, the modulus of kz is the modulus of k times the modulus of z. So therefore, let's say k was 2, you'd get 2z. If k is 3, you'd get 3z. In other words, there is a scaling by a factor of k. It'll be k times bigger. If k is 2, the length of this will be 2 times bigger. If k is 3, it'll be 3 times bigger. Okay? That's what that means. Now, that's if k is positive. Well, actually, now we're going to look. If k is positive, it'll be along the same line. But if k is negative, is a negative real number, then the direction from the origin O to the point representing kz, so that might be z, kz might be sitting up here now. But if k is negative, I'll end up with negative kz, and negative kz is 180 degree, it's point symmetry, like it's rotated 180 degrees from where it is. Because, I'll tell you why. So if k is a negative real number, then the direction from the origin O to the point representing kz is opposite, I'll explain why, is opposite to the direction from O to the point representing z. So this is what we've got. If z is here and k is greater than 1, kz might be up here. Negative kz will be down here. Okay, opposite. Now, reason is, if you get negative kz, doesn't negative 1, reason is negative 1 equals I squared. Do you know what, when you multiply by I, we did this, I think, you're rotating by 90 degrees every time you multiply by I. So you multiply by I once, and you multiply by I again. And that's why you're ending up 180 degrees on the other side. Or if you just even did it, if you had 2 plus 3i, and you multiplied it by minus 2, you'd end up in, let's say you've got 2 plus 3i. If you multiply that by minus 2, you'll get a minus 4 minus 6i. Minus minus is in this quadrant. Does that make sense? Okay? So we first looked at multiplying a complex number z by a real number k. Next is multiplication of a complex number z by I. So if you're multiplying it by I, then the argument of iz will just be the argument of I plus the argument of z. I is here. Okay, so the argument is the angle from the positive direction of the x-axis. What's that angle? Pi on 2, it's 90. Okay, see, this is real x. This is a real value, sits here. I sits up there somewhere. Well, at 1. That's where I is, up there. This is a real negative value, and this would be negative I down here. Negative I is just negative 1 on the y-axis. So arg of iz is arg of I, which happens to be pi on 2, plus z. Okay? Now, the modulus. So we've looked at what's happened to the argument. So the angle, if you know if you multiply by pi, girls, you already know you rotate 90 degrees. Anti-clockwise. We already know that. because we've looked at that before. So do you think the length of the line, let's say your complex number is sitting here, and if I multiply it by I, it just means I rotate it 90. The length is not going to change. So the modulus of IZ is the modulus of I times the modulus of Z. Now, what's the modulus of I if it's sitting at 1? Remember, I is 1I. What's the modulus of I? What's the length from there to there? Yeah, which is 1 times mod Z, which happens to be mod Z. So what that means in plain English is that if you multiply a complex number by I, and we've done it before without this, we're just trying to do it via geometrical representation. So if Z was here, it's just going to rotate there. So if that's Z, a 90-degree rotation gives me ZI, and that length there is the same as this one here. That's all that we've spoken about. Okay, so if Z's here, I know I is there, and you multiply it by I, then you're just rotating it anti-clockwise 90 degrees. So multiplication by I causes an anti-clockwise rotation by pi on 2 about the origin, and there is no change to the modulus. Next, what happens when we multiply a complex number Z by Ki, where K is real? Now, Ki would be something like 2I. Got it? Or like Ki might be up here. Or Ki could be down here if K is negative. See? Multiplication of a complex number Z by Ki, where K is a real number. So what we've got to do, it's a combination of multiplying by K and multiplying by I. So multiplying by Ki combines the two cases above. The multiplication by, so what happened when you multiplied by K? What happened to the argument? Arg of Kz was just the same as Z, as the argument of Z. Multiplying by K doesn't change the argument, but multiplying by I does. So here, we're combining the two cases. So if you multiply by K, there is no change to the argument. But if you multiply by I, there is an anti-clockwise rotation about O, the origin, by pi on 2. So therefore, if you multiply by Ki, you get an anti-clockwise rotation about O, the origin, by pi on 2. And multiplying by K just means you scale it by a factor of K. Now, if K is bigger than 1, it'll get longer. Like, if K was 2, it'd get double the length. But if K was a half, your length would be half of what it was. Look, we're going to do actually examples with this now, and I think you'll get it a bit better. All right? So we anti-clockwise rotation about O, the origin, by pi on 2. That comes about from the I, because multiplying by K doesn't change anything. And then scaling by a factor of K, because when you multiply by I on its own, it's just like multiplying by 1, and it doesn't change the value. See here, modulus of IZ is just the same as the modulus of Z. It didn't change it. Because I is 1I, and its modulus, it's because here the modulus of I equals 1. Because I is 0 plus 1I. Modulus is the square root of x squared plus y squared, which is 0 squared plus 1 squared, which is 1. You sure? Okay. Wish I had some room. And I'll just show you here. Modulus of I is 0 plus 1i. 1. So just showing the modulus of I there, how it's calculated. I've got 8% still. Okay, so this one. So we've just done that. Okay. Multiplying by I doesn't change the modulus, it changes the argument. Multiplying by K, we okay with this? Multiplying by K just changes the modulus, not the argument. Okay? Now, here we go. Multiplication of a complex number Z by another complex number R cis theta. Well, what happens to the argument? Don't you just add the arguments? So it would be arg Z plus the arg, well, whatever theta is actually, It would be arg z plus the arg of r cis theta, which is arg of z. Now the arg of r cis theta is theta. It's just the angle. And modulus of z times r cis theta is the modulus of z times the modulus of r cis theta. Modulus of z is just modulus of z. What's the modulus of r cis theta? It's staring you in the face. That's the modulus. Theta's the argument. So the modulus of r cis theta is r. So therefore, to multiply by r cis theta, you rotate by theta anti-clockwise. Remember, it's always anti-clockwise. About the origin, and then scale by a factor of r. See, it's whatever arg z was plus theta, so you add theta on, and whatever the modulus of z is, you'll times it by r. So it'll be, if r is bigger than 1, it'll get longer. If r is smaller than 1, it'll get shorter. Now, what I want you to do, I want you to try example 1. And you can actually do it with points. Now, we've got 3 plus 2i. Luckily, it's sitting right on the grid. So there's z, which is 3 plus 2i. Now we want z bar. Have we done this before? Z bar is a reflection. Isn't z bar 3, do you remember what it is? 3 minus 2i. It's just a reflection in the x-axis. Reflection in the x-axis. 2z is scaled by a factor of 2. I mean, you can check it and you'd get that 2z is 6 plus 4i. And if you draw it, but you don't need to. See, you're going 3 across 2 up, just go another 3 across 2 up, and you would be, do you get it? So you actually don't have to work out what it is. We're just trying to do it by knowing that 2z is just scaled by a factor of 2, okay? Then minus z is down the other end. You know how we said it's multiplied by, see, minus z means that it's scaled by a factor of what? 1. But the reflection of z through 180 or through pi on 2. So it would be the reflection of z back through 0, I suppose. So through 0, but reflecting at 180 degrees. So basically, if you're going 3 up there, 3 down, it's down here, the same distance. That's minus z. Get that idea? Because it's multiplying it by -1, which is multiplying it by I squared, which is 90-degree anti-clockwise rotation, 90 degrees anti-clockwise rotation, or you could look at it really as -3 minus 2i, but we're not trying to do it that way. We're trying to do it with just transformations, okay? Not by working out what it really is, like what it is. See, minus z, that's what it is.
So is it
now,
a factor of 1?
Yeah, it's a factor of 1 because you're not changed. See, 2z was a factor of 2. Minus z is multiplying it by -1. So the factor is 1, but then, yeah, so the size of it's the same. The distance from there to there is the same as the distance from there to there, but it's the rotation takes care of the negative one.
Yeah.
Isn't IZ just Z rotated pi on 2?
Yes.
Anti-clockwise. Be careful now. Watch how I'm doing this. 3 across, 2 up. Along that axis, you go 3 up. So the idea is to go 3, 2. And this one's not in the right place. 3, 2.
Maybe that's 2. Oh, no.
1, 3, 2. I think my lines aren't very good. Anyway, let's have a look at IZ, what it would be. Wouldn't it be 3i plus 2i squared? Wouldn't it be minus 2 plus 3i? That's what IZ is. IZ is minus 2 plus 3i. So it is minus 2 plus 3i. Just my line is not in a good place. I'm sorry. That line's drawn badly. Next time I've got to fix that one. Okay. So, girls, 3, 2. This is how you do it. You go 3, 2 along the axis. So along this axis, 3, 2. 3, 2. Sorry, it's just So this is IZ. You can check by working out IZ if you want. And it would be minus 3 plus 2i squared, which is minus 3, 3i minus 2 it would be. Now, negative a half IZ, there's a few things happening. Tell me, why have I just got that? I should have more stuff there. It's scaled by a factor of a half. It's also the 90-degree rotation is the I, and then the negative is another 180, the negative 1. So it must be, if it starts here, it's going to go 90 and then another 180. I think it's Z bar. No, it's not. It's here somewhere. I think it's here. I reckon it's there. Let's have a look. We know where IZ is. It's here. So it's the negative of that, so it's back along that line, which I didn't draw very well. Do you know what I mean? And then it's half the size. So scaled by a factor of a half, but then it should also be, in the book it actually says scaled by a factor of negative a half, but it's half the length, but it's rotated 180 about the origin. Do you get the idea? So if this is 3, 2, it's going to be 1.5, 1. Do you get that? 1.5, 1, 1.5, 1. That one's in the right spot. 1.5, 1. It's here. There it is. See, half the length of 3, 2, do you get what I'm saying? Is 1.5, 1. So I've got to do it twice. 1.5, 1. That's a 90-degree rotation. 1.5, 1. We're down here. And it should be on that line, but my line wasn't drawn very well. It must have, whenever you use a Mac and go from wherever to wherever, it always changes. So this is negative a half IZ. Now, what you can do, just to check, why don't you just do negative a half I times what your Z is and see what you get. And we think that we're getting 1 negative 3 on 2I, according to this. So what do you get? You get negative 3 on 2I minus 2I squared on 2, which is plus 1, which is where we said 1 minus 3 on 2I. Does it? All right, but look, we're trying to do this by transformations, not by multiplying through by I and stuff like that, but we can check it doing that. All right, now Z squared. We'll have modulus what? Remember, Z is r cos theta. So won't it be modulus of Z times modulus of Z, which is modulus of Z squared? See, if Z is r cos theta, then it's r cos theta times r cos theta. The modulus will be r squared. So it's got modulus of whatever the modulus of Z is, squared. And the argument will be theta plus another theta, won't it be? Because it's r cos theta. What we're really doing is r cos theta times r cos theta. Don't you multiply the moduli and add the argument? So argument theta plus theta, which is 2 theta. So where is Z squared going to be? If this is its length at the moment, 3 across 2 up, you'd have to work it out by, yeah. So what's its length? Yeah. What's it? It's the square root of, 13 is Z. So therefore it will be 13. Because it's root 13 squared, which is 13. Okay. So I don't think I've got 13 units along there. I can't do it. Okay. And the argument will be 2 theta, just double whatever the argument is at the moment. I think it's up here, somewhere up there.
Yes.
Okay, somewhere up there. Whatever gives us 13. 9 plus 3 squared, I'm trying to think. 2I squared, what do you get? 9 plus 12I plus, and you're probably right, plus 4I squared, which is minus 4. Thank you. 5 plus 12I Yes, there you go. 5 across, 1, 2, 3, 4, 5, 12 up, sitting off the thing. The continuation there somewhere. Notice if this is theta, 2 thetas all the way across there. Okay, what's this one? Z squared, somewhere up there. Okay, now if you multiply a complex number by another complex number, don't we just multiply the moduli and add the arguments? So, what's the modulus of 1 plus root 3i? We actually have to work it out. 1 plus root 3i is up here. That's 1 plus root 3i. Isn't it tan of 60 is root 3 on 1. So modulus 60 is pi on 3. It has modulus pi on 3. Yeah, that's the argument. Thank you. What's the modulus? 2, because square root of 1 squared plus root 3 squared is 2. Modulus 2, thank you girls, argument root 3 on 2. So therefore, to find 1 plus root 3i times z, it's found by, what do you do to the modulus? If this is 2, isn't it doubling the modulus or multiplying the modulus by 2 and rotating by? So doubling, because it just happened that the modulus of this one was 2. So it'd be the modulus of this one times the modulus of the other one. So doubling the modulus and rotating anti-clockwise by pi on 3, which is 60 degrees. For some reason, I've done another one, but with a different z, okay? So, but try and do it without using what z is. So, look, we'll just have to sketch. Oh, no, it's a negative one. See, negative 1 plus 2i, that's why I did it. So there's your z2. Remember, it's a subscript. Where would z bar be? Reflection in the x-axis. So it would be z bar would be down there. Where would 2z be? Along the same line. But instead of going 2 up or 1 across 2 up, you do it another 1 across 2 up. Okay? That would be 2z2. Would be up there. Scaled by a factor of 2. No change to the argument. Negative z is z scaled through a factor of, yeah, I think they put negative 1, but 1. And it's the reflection of z through O. So you're basically just reflecting it back through here. That's negative z. It's just reflecting it. Actually, I think they write scale by a factor of negative 1, actually, girls. They do, yeah. But the size stays the same, but it's just reflected. Yeah. Like you can say scale by 1, but then reflected if you wanted, but yeah. IZ is Z rotated, you know this one? Pi on 2. So this is now just looking at it. So look how we get to that. I always go along the axis. Look, up 2 across 1, along the axis 2 down 1. It's there. So that would be IZ. See, later in further exercises that I've got here, we don't give you any numbers. You're just going to have to be able to do the things. And minus a half IZ is IZ, and it's on the opposite side, and it's half the length. Got it? So you take IZ, and it's scaled by a factor of negative a half. So you look at where it is, which is 2 and 1 down, 2 across 1 down, but it's got to be over here instead of 2 across 1, and that's not drawn, that's got to be fixed. We go 1 and a half. So 2, 1, 1 a half is half those measurements. So this would be negative a half IZ would be there. Notice the distance from O is a half, and it's on the opposite side of O. Okay? And Z squared, we know, has a modulus of whatever mod of Z is squared, or mod of Z squared. Same thing. And the argument, remember, it's r cis theta times r cis theta, will be, what's the argument? 2 theta. You add the arguments. So that's just the same as what we did, but it's probably good to go through it again. And remember, we did this, I don't know why I did the same question again. Exactly the same numbers, but I did. So 1 plus root 3i, remember it has a modulus of 2 and an argument of pi on 3, 60 degrees. So it's just found by remember what it was? Doubling the modulus or timesing it by 2 and rotating anti-clockwise by pi on 3. Next time I'll put different numbers in that or something, or do something different actually. Yeah, I'll get rid of it, I think.